Alright, in this video I'll be looking at the deductions from Newton's second law of motion. And I've already stated Newton's second law of motion. I've taken some time to explain and to kind of break down that Newton's second law of motion, that the applied force is directly proportional to the rate of change of momentum, and that applied force F is given as momentum change, final momentum minus initial momentum over time taken. That is, momentum is defined as a product of mass of the body and its velocity. So why we call this final momentum? Because this is the final velocity. The mass of the body in this case does not change. And this gives the initial momentum of the body. So if you have not watched the first and second video, I know the analysis I did on Newton's second law of motion, applying this equation F is equal to ma, I want you to quickly go and look at that video. I did a lot using this equation, solving equations relating to dynamics of motion of a body. Now we are looking at the deductions from Newton's second law of motion. And this is a mathematical equation for Newton's second law of motion, that the force applied is equal to the rate of change or momentum of the body. And again, this equation defines what a force is, apart from the fact that Newton's first law explains what a force can do, that the force is needed to accelerate a body, to change the direction of motion of a body, and also to decelerate a body. Newton's second law says that the force that acted or that acts on the body is given at the momentum change of that body, or the rate of change of the momentum of the body. Now, the first deduction I want to get from here is the impulse. What is impulse of a force? Impulse is more like a blow. It is the product of force and the time during which the force acts. We call that the impulse of a force. Okay, so it is given as product of this. And if I come back to this equation, I have Ft. If I cross multiply this equation, I have force times time is equal to momentum change, mv minus mu. It therefore means that the impulse of a force, the impulse received by a body when a force acts on it for some given time, is given by the momentum change of the body. It means that the impulse of a force will have the same unit as momentum change. Unit of impulse will be given as Newton second. Okay, so let's see a case where a force of, let's say, a force of 5 Newton act on a body, act on a body for, let's say, 0.5 seconds. What is the impulse received by the body? A force of 5 Newton act on the body. The impulse received by the body is the product of the force and the time taken. That is, this time t is the time during which the force acts, or during which the force is in contact with the body. That is talking in terms of contact force, because the contact force requires contact with the body that it affects. So that gives me 5 times 0.5, and the impulse received by the body is 2.5 Newton second. Okay, so that is one case of the deduction from Newton's second law of motion. Or sometimes can have a case where, let's say, this hockey stick is used to hit a ball or hit a ball, and with a force. Let's say the force that is exerted on the ball by the hockey stick is 10 Newton. And if the force or the time of impact, the contact time between the ball and the hockey stick is 2 seconds, that is, the force acts on the ball for about 0.5 seconds. So what is the impulse received by the ball? The impulse received by the ball is also given as a 10 times 0.5. That gives you 5 Newton. Now, this impulse will cause the momentum of the ball to change. Let's say the ball was initially at rest, because the impulse received by the ball will cause a change in the momentum of the ball. Let's say the ball was initially at rest. Let's say this is a ball, and the hockey stick is applied to it, and the force exerted on the ball through the or with the aid of the hockey stick is 10 Newton. Now, this 0.5 is the contact time, between the hockey stick and the ball. Now, it will cause momentum of this ball to change. If initially the ball was at rest, it means the initial momentum of the ball, this is the mass of the ball, multiplied by its initial velocity, will be equal to 0. Since the initial velocity of the ball is 0, it's at rest. Now, this ball will move away with a given velocity. So the impulse received by the ball will result in the change of momentum of the ball. It changes from 0 to a value which is non-zero. Okay, so given that the mass of the ball is 0.05 kilogram, it means that the impulse received by the hockey is equal to mv minus mu, and since the initial momentum is zero, so the impulse received by the ball is mass times velocity, and we can find the velocity with which the ball moves away as the impulse, which is 5, the impulse here 5 over 0.05. So that is 500 over 5, which is 100 meters per second. It means that this ball moves away with a speed of 100 meters per second. Okay. Now consider this question. When taking a penalty kick, a footballer applies a force of 20 newton. Okay, as I read, let me write down the given parameters. The force applied to the football is 20 newton, just like the case a football match is being played between two teams. So there's a penalty awarded to one of the teams, and the player applies a force of 20 newton through his boot on the ball. And the contact time, that is the time during which the boot is in contact with the ball, that time t is always called the contact time, okay? 0.3. And if the mass of the ball is 0.05 kilogram, the question says calculate the speed with which the ball moves away, that is from the penalty spot towards the goalpost, as if the player should score a goal. Okay, this is the goalkeeper and so on. All right, so here we see that we applied the Newton's second law of motion equation to solve this. That the force applied is momentum change, rate of momentum change of the ball. Okay, now since this ball was at rest before the force was applied to kick it towards the goalpost, it means that the initial speed of the ball will be zero, and the initial momentum is also equal to zero. So it means F becomes mv divided by t. So we want to find the speed. The speed of the body from this equation, making that subject to the equation, will be ft divided by the mass of the body. That gives me the force is 20 newton times the contact time 0.03 seconds divided by the mass 0.05 kilogram. So that gives me 20 times 3 divided by 5. So my answer is 12 meters per second. So this ball moves away towards the goalpost with a speed of 12 meters per second. So this is another question that has to do with the applications of Newton's law of motion, that is using the equation that defines what the force is. All right. I guess you fully understood that. Now let's see something else. We'll talk about momentum change of a body. Momentum change. Now, if a body was initially moving along a straight line, let's have this case when a body of mass is moving with an initial velocity u along a straight line. Now, if the momentum of this body must change, a force must act on it. And what the force does is to change the velocity of the body or the speed of the body from initial value, maybe initial velocity is 20 meters per second, to change it to a speed of 30 meters per second. So for the speed of the body to change along this straight line, it means a force must act to cause the body's velocity to change from 20 to 30. So that the momentum change of this body, that is delta rho, is given as final momentum minus initial momentum. Okay, so that gives me 30 m if the mass is not yet given, minus 20 m, where m is the mass of the body, meaning momentum change of the body is 10 m Newton second. Okay, so this is taking place in one particular direction along a straight line. There's no change in direction. The only parameter that changes is the velocity of the body from one initial value of 20 to a final value of 30. What happens when it is this case of momentum change? But this time around, there's a change in the direction of motion. Let's say there is a particle of mass m moving towards a hard wall, a solid wall with an initial velocity u, okay, towards the wall. And then when it arrives there, it makes this head-on collision. That is, with the wall, it hits the wall and rebounds with the same speed, probably the same speed u, okay? So they may ask you to find the momentum change of this particle, towards the wall. Is moving with the speed of, initial velocity u may be 10 meters per second, 5 meters per second, as case may be, and then it makes this contact with the wall and rebounds from it with the same speed, So what's the momentum change of this particle? Some students may make the mistake of just saying momentum change is zero, because since there's no change in velocity, okay, they may want to write it like this and say final momentum. They want to write it like this and say final momentum mu minus initial momentum mu is equal to zero. But this is very, very wrong. So in your own notes, write it like this and place this sign to show that this is wrong. Now, why is this wrong? Why is this capital wrong or completely wrong? Because here, consider that there's a change in direction, and the momentum change occurs at the point where this ball is in contact with the wall, at the point where this particle is in contact with the wall. Now, when the particle was moving towards the wall, the direction is to the right, and we decide to give that negative. The direction of the speed of the particle is to the right along the positive x-axis. I can decide to give that negative sign to indicate the direction to the right. And after its collision with the wall, after the impact, after the contact, it moves away in this direction, that is towards the negative x-axis. I can call that positive. So you can see that the two speeds have different direction, meaning that my momentum change, which is final momentum minus initial momentum, will now be written as what? This my final is m times positive u, because it rebounds with the same velocity u. That gives me positive, okay? Minus the mass of the body is m. That gives me m times minus u. Why is this? So this negative is because the initial velocity u has, the direction that's already assigned negative. So the direction of the initial velocity is negative because I assign negative sign to the speed of the body in the direction of the positive x-axis, and assign positive sign to the direction towards the negative x-axis. Okay, I'll do that so that I can have positive momentum change. Okay, so this gives me mu minus minus gives me plus mu. That gives me 2 mu. So whatever the mass is, whatever the velocity is, I can make my substitution and find the momentum change of the particle. Please take note. And this question, if you're not careful, you can make the mistake of just subtracting them. So notice the change in direction. The two directions are different, and they will have to use different signs, negative and positive, or positive or negative, as the case may be, to indicate the direction of motion of the body. Okay, so this is one way that an electron or an atom, a gas molecule, exerts pressure on the walls of their container, because momentum change must be non-zero. If there's no momentum change, how will the molecule of a gas exert pressure on the walls of their container according to kinetic molecular theory? Because that assumption says that it is because of this constant collision, the frequency of collision of the molecules of this gas against the walls of their container, that results in the pressure of the gas. So this is how it does. Now, how about the force exerted from Newton's third law of motion? In the course of this particle making contact with the wall, it has transferred some force, it has exerted some force on the wall. And the force exerted by the particle on the wall is given by its momentum change divided by the time. That gives me 2 mu over the time t. So if this time is the time of impact, that is the contact time between the particle and the wall, if that is known, I can find the force. And this force that the particle exerts on the wall is the same, according to Newton's third law of motion, as that which the wall in turn exerts on the particle. They say action and reaction are always equal and opposite. So let's call this the reaction from the wall, and this is the force that is exerted on the wall by the particle. The two forces are the same, and it can be calculated using this equation or expression. So that is from another deduction from Newton's second law of motion. Now, sometimes you are given this case where a body of mass 20 kg is moving towards a hard wall with a speed of 5 meters per second. Sometimes the motion may be downwards. You see a ball of mass, the same 20 grams or thereabout, moves with a speed of 10 meters per second towards this. Now, it's possible that when it hits the floor or the hard surface, it may rebound. If the collision is inelastic, it may rebound with a speed that is less than 10 meters per second. Let's say with the speed of 8 meters per second. Okay, here we see there's a loss of kinetic energy or thereabout because when it was moving towards the hard surface, it moves downwards with a constant speed. Let's say, for instance, with the speed of 20, with the speed of 10 meters per second. That is the speed of the ball just before it makes contact with the floor and then rebounds with a lesser speed, a speed of 8 meters per second. How do we find momentum change, of this object of mass 20 kg? So the momentum change in this case is this the final momentum minus the initial momentum. We always state this equation as the equation for the change of momentum of the body. But here we see that, let's say direction downwards is the initial direction, while the ball was moving towards the hard surface. Let's call that the initial direction. And then when it's now moving upward after the rebound, it's moving in the upward direction. Let's call that the final, situation of the condition of the body of mass m. Okay, so my initial velocity, my mass is, okay, let's start with that, 20 grams in kilogram, that gives you 0.02 kilogram. Okay, so my initial velocity u is 10 meters per second, and my final velocity is 8 meters per second. Now, what do I do here? The two directions are different. When it was moving towards the earth surface, it moves in the downward direction. I can decide to give that negative. Then the upward direction after the rebound is positive. Okay, so I can have the momentum change is equal to mv minus m. My initial velocity, since it is downward, is minus u. Okay, that will give me mv plus mu. Okay, so I can factor out my mass, which gives me a final plus initial. So, okay, so that gives me 0.02 into 8 plus 10. That gives me 0.02 times 18. Of course, that will give me 2 times 0.18, which is 0.36 Newton seconds. So that's momentum change. For this case, then the same thing applies to this too. You have to also show by using the signs. You can decide that let's give this negative sign and this a positive sign so that momentum change in this case is also mv minus mu. Okay, so the mass of the body 0.02 kilogram. Okay, initial velocity, direction towards the wall. Let's call that the initial direction. The initial direction, I can give that negative sign. That gives me u equals minus 5 or thereabout. And then my v is plus 3 because direction away from the wall. I give that plus 3 meters per second. Okay. So the momentum change here is now given as mv minus m into minus u. That gives me mv plus mu. Okay. Now that gives me 0.02 into the two speeds. Okay, that is 5 plus 3. That gives me 0.02 times 8. That gives me 0.16 Newton second. That gives the momentum change of the body. So whatever case, as long as it involves change of direction, you have to still note that the change momentum equation becomes positive. But if the momentum change happens, along a straight line, that means momentum change will simply be mv minus mu because that only involves change in magnitude and not direction. Okay, we'll see more in the next video.